Hello, everyone. Welcome to the binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Heads up, this will be our last podcast of the year until we return on January 9th and 10th. But yeah, we do have some topics today around some browser bugs and a Project Zero post on a kernel exploit, as well as a pretty cool Huawei chain. Before that, though, as always, I'll let Z get into the Spot the Vuln challenge, the last one of the year.
Yeah, and this Spot the Vuln challenge actually kind of took me by surprise too. I decided to use the AI to support generating some of these this time again, and I had an idea for one. What I was looking for was kind of a mass assignment sort of idea. So that's what we have in this code. Um, so what this code is doing, you've got this up. It's a PHP code, takes in the PDO objects. I didn't really want to include that in here. Um, Called update settings. The idea is you might have like a settings page on your web app or whatever, and it just sends in a bunch of fields and their new values. And this thing will take all of those fields, place them into the or match them up with their placeholders, place it into the SQL query, prepare it, bind all of the fields that you gave it, and then execute. So the potential problem there when you see this code pattern is, well, is there any field that you can set like this that isn't exposed in the UI? So classic example, since this is update users, there's a good chance there's something like the password hash that you might be able to update. Probably not something you should update, at least not like directly like this, but like you could break things like that. If there's any sort of privileges, you'd be able to go in that route. So that's one solution to this. If you saw it, like that's a valid solution. I don't include any indication of what those other fields may be, because the way the bot actually gave me this and implemented it, I'm like, isn't there a different injection here? And I played around with it and thought it was kind of an interesting setup. The other thing that exists here is in creating the placeholders, it's creating the string, and these fields are largely user controlled, although they do have to be valid fields parsable by PHP. And that ends up directly inside of your query. So we're using a prepared statement, but this one part that's just taking the field name equals colon field name, saying like it's a named parameter and binds them later using the same. It places that inside of the string or inside of the raw query. So in theory, you could have some sort of injection here. The challenge is even if you do that, it does this whole for each fields, and it's going to iterate over every field you provide it. And whatever your payload is going to be a value that gets bound. And it's going to try and bind it. And then when you execute it, at least on my test instance, it would fail because you had bound a value that wasn't in use. So then I started wondering, well, is this actually even exploitable? I had this one issue with the mass assignment, so I was happy to kind of put this out. But I wanted to see if anybody else would come with a way to actually exploit this one. And I kind of did leave it where I'm pretty sure there's got to be some trick to do it. I just didn't know it when I actually put this up yesterday. So what I did come up with that kind of worked on my test instance was you could get it by basically breaking the bind value. This can return false and the return value isn't checked. And you can break that by having a sufficiently long field name. I tried it with about 2,000 characters and it failed there. I'm not sure what it needs, but 2,000 characters is sufficient to kind of get that to return false so it doesn't bind to your payload and everything else works as is. So you can exploit it. The fields are sufficiently flexible. You can't use spaces, so that is another little trick, but you've been able to do SQL injection without spaces for quite a while. You're unaware of the trick, just doing like a // a comment and then end the comment, it gets replaced in SQL engines with a space. And that's also a valid key, surprisingly. I was a little bit surprised by that. I guess one other interesting thing here is in some cases the bind value doesn't or is a little bit more flexible. It depends on the actual setup on the server. And in those cases, you can actually rebind something like the user ID to be another value. So you could update settings of another user. But that does require this is running with like emulated prepared queries, which ideally you just don't do. Let the server do that, but it's not that uncommon also to see it. But yeah, so there's a few ways you could exploit this one. And I kind of genuinely had a little bit of fun solving this one myself, at least on the exploit side.
Yeah, it's pretty funny that like you were able to take some time out and try to exploit your own challenge in a way, or like a shared challenge between you and the AI. So
Yeah,
yeah, it's kind of interesting.
The AI refused to believe that there was SQL injection. I tried to explain it, but I mean, it's a computer, so
Stupid computers. Yeah. All right. So we'll get into our first topic here, which is a type confusion in Internet Explorer's JScript 9 engine, which was reported by Project Zero's tag or threat analysis group. So presumably something that was found in the wild. Um, the RCA contains a POC which does some interesting things, which I'll go over, kind of go over the POC and get into what the issue is. For those who can see on screen, you'll notice that they create a few objects. They create a array buffer, which is assigned G, and an int32 array assigned D, which uses the array buffer as a backing buffer. They also create this E object, which has some properties A through E. That's important for the type confusion later, but not really super relevant for the vuln. Then they call this boom routine a bunch of times to get it hot path. I think they call it like 100,000 times. That'll cause the engine to JIT it, and it contains an M parameter. If M is set, it'll switch out the int32 array instance for the E object, and tries to write to its 0 entry. If it isn't set, it'll just read the first like value in the int32 array and then do nothing essentially. So yeah, they call this boom function 100,000 times with M set to false, and then they call it once with it set to true. And what's going on here is the JIT compiler generates some code that does a type check on that Q variable to ensure it's an int32 array. Because obviously they don't want the type being switched out from underneath it while it's doing some like JIT operation. It has to make some assumptions. But by calling it so many times without switching the type, um, I believe the JIT compiler assumes that like, okay, this type isn't going to change. Let's just remove that type check in optimization stage. It's not important. But then when it gets called the 100,000th and once time, it switches out the type, assumes it's still writing to an int32 array when it's actually writing to whatever this e objects dot e field points to. Because of the type confusion, it goes to right there thinking that's the pointer to the backing store, but actually it's completely user controlled. And yeah, that gives arbitrary right because of the type confusion there. So fairly understandable what the basics are of what's going on there. They do go a little bit into the deeper like cause, and they root caused it to this opt array source optimization phase, and it would call should expect conventional array index value, which for whatever reason that function would sometimes return false. I'm guessing it's because they trained it with the 100,000 times and it made it think it wasn't necessary anymore. They don't really go into like the details of what that function does, but the fact that it can return false means that the code that keeps the type check is essentially omitted, gets stripped out, and that's what can cause type confusion. So it's a little bit of a simpler vuln as far as JIT bugs go. I was a little bit surprised, though it is JScript 9, so this is the kind of bug you would expect to see in like Safari or something like a couple years ago, I would say. Yeah, as far as JIT bugs go, this one seems pretty simplistic. You're just training the JIT to think that it's the type check isn't necessary when it is still, and like the assumption can still be broken. But
yeah,
yeah, it's kind of a fun bug.
definitely one of those JIT bugs that like it's a lot easier to understand this bug than some of the Chrome bugs we've seen. Out of Chad XCD80 mentioned J9. I thought they were using Chakra. So that's actually something I found out about kind of recently. Because I remember something else coming up about JScript and exploitation in it. I think it was like I think it was some other type confusions. Either way, it came up and I'm like, where's this still being used? I mean, who's still using Internet Explorer? Well, it turns out it's still being used in Office. Inside of like Office documents, they're using the JScript engine there. So That's still actually a pretty big attack surface that it's getting used in. They're not using Chakra yet. And that's where this was also found, was that this is being exploited via a remote office document loading HTML containing the JavaScript.
Yeah, it's a pretty interesting attack vector that you might not think of right away. Because yeah, like Office documents just support so many features, and of course, it is something that's going to be used a decent bit in enterprise environments. Depending, they might use some alternative software, but Office is still pretty popular. So yeah, it makes sense that this was found in the wild and would be targeting something like Office. It is a fairly well targeted attack surface, and yeah, I mean, who knows how long it'll take for Office to upgrade to not using JScript 9, and even if they do, a lot of companies will run older Office anyway, so this is an attack surface that's going to stick around for a long time.
Yeah, I
It's
mean
just one of those things.
legacy is a big deal for Microsoft, and that legacy support. So that's probably why it's still being seen. I am like a bit surprised that it's not using even like Chakra Core. Even though I mean they've even moved Edges now, on Chromium. So
Yeah, even Chakra's dead now.
yeah. Actually, I'm not
Yeah,
sure. Is development fully dead on Chakra?
I think so. I think it's
Okay,
frozen.
I've never actually looked into that, but yeah, I
Yeah.
mean, apparently JScript is still kind of getting some use at least.
Yeah, Rudimal mentioned sad Edge Chakra got scrapped. It was actually kind of good. Yeah, I heard some, like, I didn't really go full bore on researching Chakra. I did know some people who got interested in it. Um, yeah, it kind of sucks. Chakra was a neat thing, and it always it's never good when like a something like a browser engine or anything like that exits the market, because when Edge switched to Chrome, it means the Chromium codebase is even more like dominant of the market, and you know there's a few reasons I think that's not really good, but I won't really go into that here. But yeah, it sucks. Chakra was neat, and it sucks that it got scrapped. It will be interesting if Chakra is used for, like, I don't know if they would use Chakra for Office in the future, or if they might just go up to their Chromium fork. I don't know exactly like what would make more sense for something like Office, but maybe it'll be resurrected for something like that. Who
I
knows?
would hope they take it up to V8, honestly, like get it on the
Probably
Chromium,
they probably would. Yeah,
just in the sense of active development and having people already kind of working on that. It just makes sense to keep them a bit more centralized. And of course, getting any fixes from the V8 team itself.
yeah. Um, but yeah, kind of a neat bug. It's a little bit surprising how easy it is to get to an immediate exploit, because a lot of the times in browser chains, your initial primitive is a bit weaker than this, and you have to chain a bunch of steps to be able to get a relative read write. This essentially gives you like a read write out of the gate. So yeah, you could probably exploit this pretty easily, and it might be a fun hobby project to do over the holidays. Maybe just take this to like code execution or something, um, which they actually explain the exploit strategy for of how you could do that, which is something I kind of skipped over. But yeah, towards the exploit section, they talk about how you could use the type confusion to hit the length of an array object, get a relative read write, um, set up a little fake literal string object to get arbitrary read write, and then hit a v table. So yeah, I mean they kind of lay out how this could be exploited, and yeah, and Office would be an interesting vector to try. So pretty cool post. And yeah, it's kind of indicative that there's probably other similar um, types of JIT bugs that are pitable through JScript 9. So we might end up seeing more coming out of that in the future.
Yeah, so they kind of touch on that actually when talking about how, as is usual with these RCAs, how this phone might have been found. They call out that it's very similar to a 2021 bug that was found through fuzzing. So this could have been more fuzzing, or it could have been variant analysis starting from the prior bug.
Yeah. Yeah, I always love the types of details the RCAs go into. So yeah, pretty cool bug. Continuing on with Project Zero stuff, we have a post by Seth Jenkins, which is a new member of the Project Zero team, on an exploit for a vulnerability that was discovered by Jan Horn in the Linux kernel's memory management subsystem, which was fixed in September of this year. They don't really go into the details of the bug, and it is a pretty complicated bug and root cause and whatnot. So it mostly focuses on the exploit, assuming uh, what the bug leaves you with in terms of primitives. But yeah, Z, I'll let you get into this one.
Yeah, and this one I thought was pretty fun to read. You mentioned we saw the Project Zero, like their bug tracker reports for some of the memory management bugs that were getting reported by a Gen Horn. And this ends up being just kind of an exploit on one of those. Kind of setting the scene here, we start off, or the vulnerability as it relates for this exploit is in this folio lock anon VMA read. And you're in this state following the vulnerability that you have a use after free in here, 'cause this folio mapping value, the pointer that this is pointing to, that has already been freed. And so when this thing does the whole VMA or calculation to find the non VMA, which is the basic offset from the mapping that it reads, it gets that, and then it reads a value out of it called the root anon VMA. So basically, because of the use after free, that root anon VMA would be an attacker controlled pointer. There is a bit of work that has to be done to actually make this attacker controlled. So the anon VMA, as you might guess, is an anon VMA structure. So that is stored off in its own Kamela cache, which just means like usually when we talk about what else is in the same allocation cache, when it comes to use after free, like we'll talk about like KL 64 or something is like its cache size, then there's a bunch of objects in there that he might be able to overlay. When you get everything in its own cache, you can't really do that. They're all the same object.
It's harder to do like a type confusion, basically. Yeah.
Yeah, it takes a bit more work. If you've got memory pressure, though, the idea is, and what they end up going with here is effectively you apply that pressure and you get like an entire page allocated and freed. And with this one use after freed object in there too. And your goal is just to get the backing page actually, or like in the slab, the memory page that the slab is using, to get that freed and back out so it can be reissued to some other uh slab and like get used in another cache. So you get to use somewhere else. It's a little bit more complex. It's a little bit more meta because you're kind of you're attacking or going after the management of the heap rather than just at the heap level. A little bit more meta, I guess, but conceptually, you're still getting the reuse. You're still kind of landing in that same area where you're getting control of this pointer ultimately. So coming back into the code here, you control this one pointer, and they had some options for how they could exploit. They could either follow it through, it gets returned, and maybe something else is going to use it in a vulnerable way. But you do have this immediate use of the down read try lock, which basically just takes a semaphore, or what it presumes is a semaphore, inside of the root non VMA, and it's going to try and lock it. So what that ends up looking like is effectively they've got the code in here, but it'll increment the actual count for the semaphore. It'll increment that by 0x100 depending on the bits. So it needs the lowest or least significant bits to be 0 along with the most significant bit to be 0. So basically it's not a negative number and it's aligned. And with that, it'll just increment it by 100. And you'll also notice in the original code, it'll do the lock, but it will also do the unlock. So you get a write at an arbitrary address, like you can control, but it does get reverted also, which is kind of fun. And also shout out, they called out using Unicorn Engine to understand a little bit better the try lock. And I just want to shout that out. I don't think we've talked about using sort of, I guess you could call it like a symbolic execution as a way of understanding. I guess we did do the one. I might have been a hexacon talk. I feel like we did kind of something similar on one of the watch parties where they talked about. Nonetheless, I wanted just to call out that they did mention using unicorn here for a bit,
Yeah.
just to help figure out
I also
what.
just wanted to shout that idea of the three least significant bits having to be zero and the most significant bit, especially that part having to be zero, it does introduce another limitation because you're basically locked out of using like hitting kernel pointers at that point. Kernel pointers are going to have the most significant bit set, so
Yeah,
it,
like the
it
whole
restricts your
thing.
write a little bit more.
Yeah, I was going to get into that where the whole thing is that you have a right of the address, but you're fairly constrained because of this bug. Yes, it's an increment by 100. You can make some numbers bigger, but you've got these constraints on what you can actually work with. You just said those bits need to be set is a bit of an ask, and it does create a challenge of, well, what do you target with this? And that's where they jumped into a bit of an interesting strategy. Um, in that they talk about basically how interrupts were working in the kernel. If you're familiar, you have an interrupt happen, the kernel is going to jump to some other address, it's going to change out its mappings, whatever. Um, Store all of the registers and then go along with whatever it's wanting to do, like the new code. Basically, context switching. Um, so what they notice here is basically that's not exactly randomized. The addresses that it will go to for different interrupts is a constant or is a static value, and it's stored in this CPU entry area structure. So knowing that it's not random, what they could do is use, or what they ended up using is the DB exception or hardware breakpoint. Um, they notice, this will hit that interrupt. The breakpoint gets reached, does this switch, and it dumps all these registers out to the stack, which can now be modified by this use after free. And so what they did is they targeted copy to user and copy from user calls, and basically as they would set it up so the breakpoint. I guess the important thing to mention here is that these breakpoints can be set so like a user can set a breakpoint on accessing like their memory. So that means it can be reached during a like copy to user or copy from user call. So the kernel is making a call, and the breakpoint that gets reached is something that's been set by the user. So the way they do that is they set the watch on the output buffer that like uname's gonna give its response into. Have the breakpoint hit there, use their corruption earlier to just increase the size. So what do they target? They target the address of the copy to user size. So I want to say that was RCX or yeah, RCX register. Basically the saved RCX register. They target the size of that kind of the dumped register in the stack, targeting that so that when the exception returns, it's going to have a corrupted size there, and then copy to user runs with a larger size by 100 bytes or by 0x 100 bytes, giving them basically a bunch of stack information from the kernel stack being read back. So that also lets them break KASLR, get stack canaries, actually the kernel canaries going to be visible that way, and then they can do the same thing on a copy from user. Have it hit, have it copy more data than it should, um, and smash the stack and go for a pretty traditional, just well, ROP in this case they talk about. But on the whole, I mean, it's a fun attack. Attacking it during that period while it's saved for an interrupt, I think is a really fun way to go about it. It's a cool attack. Um,
There's a lot of cool stuff here. Um,
yeah, and
I
they go
really like the way this
into
attack worked.
yeah, so do I. They go into a lot more kind of detail with it. Um, but if I mean, effectively, I am just summarizing here. They're storing the data in transit between where it's supposed to be used and that in or after that interrupt. Yeah, I really like this post. It did feel a little bit long to read, but like I like this attack. He also goes into, he does mention they patch this or suggest that they start randomizing the CPU entry area, which sounds like they've done. But then he does talk about another technique for bypassing kernel ASLR using the TLB side channel. It just kind of mentions that for a while there was a kernel page table isolation. So when you switch to the kernel, the page tables were completely swapped out. and that kind of offered some mitigation to that side channel. But because of Meltdown, um, basically they ended up just using the Meltdown mitigation, which doesn't quite protect against this side channel in the same way. Because with page table isolation, it's not mapped, so like you can't have a side channel on if it's mapped or not. 'Cause they're just not mapped. But with Meltdown, it does keep them mapped, and it just can't speculate in there with the with the Meltdown mitigations. But they went that route, and so it kind of opens up this older attack again. That almost feels like a bonus section to this whole post. And I was definitely more interested on the exploitation, but they kind of tossed that in there as a little bonus thing, so I figured I'd mention it.
Yeah, I really like that idea of hitting the save register context on the stack. It's taking advantage of something that like kernel developers really don't want to have to deal with like things like interrupts. It kind of sucks and it's annoying to deal with, and that's probably why the user entry areas, at least for a time, were mapped to like a fixed address, and they just dumped register context there. It's a bit of like a necessary evil. So yeah, hitting the register context, I like that idea. Even if the area is randomized going forward, it is something that like other exploits could potentially take advantage of too. Um, on the way to like getting some better primitives. Um, One thing I
Yeah,
thought was
and
cool. Go ahead. I'll
I
get
was
into
just going to
something else
mention that
afterwards.
that same idea of targeting the saved context is actually how I believe one of the old pack bypasses worked on iOS. Is they were able to basically get the key or whatever they needed out from the saved register.
Yeah. Um, so yeah, another thing I really liked was the way they hit the copy to and from user calls with their exception and basically targeting the size. Um, So they went with the stack here, which in some respects is easier. Like, they were doing a stack overflow, they were able to leak the stack cookies, so, it seems like kind of the obvious route. You could also attack the heap with this too. Depending on whatever you're targeting, like they went for copy to and from users into stack buffers. There is obviously going to be ones into heap buffers as well. And in a situation where you can't ROP or you don't want to ROP because ROPing in kernel sucks, to be quite honest with you, you could potentially establish some other primitives by attacking heap data too, like trying to get like an arbitrary rewrite or something. So yeah, there's a lot of different ways you could take advantage of that idea of attacking the copy to and from user calls, because it's just kernel has to do it a lot. There's going to be a lot of areas that do that. So yeah, there was a lot of aspects of this exploit that I thought were neat. And yeah, the bonus part about like a basically a permanent x86 KSLR break was pretty neat as well. It does only work on x86, and it does require like a local. You would have to have local access, so it's not the worst thing. But again, like circling back to what I said earlier, it's taking advantage of something that's just really difficult to deal with, and in this case, almost impossible to deal with. Um, so yeah, it's taking advantage of a lot of the lower level problems that you have, like at the architectural level. So yeah,
Yeah, good
really good
shout
post.
on like it just being x86. Completely forgot to mention that, but yeah, the bypass there is just an x86 thing. Uh, Nonetheless, I mean, even the side channel is kind of cool. At least to keep in mind to be aware of it because it is something that was kind of patched for a while and kind of just came available.
Yeah. All right, so we'll get into our last topic here, which is by Impala Labs. And it's about three vulnerabilities in Huawei Secure Monitor, and it's a bit of a follow up to last week's post on hypervisor, Huawei hypervisor vulnerabilities. For those who aren't aware what the Secure Monitor is, they go into a bit of detail on it on the top of the post, but it's basically responsible for bridging between the normal world and the secure world. So for those not familiar with like ARM's trust zone model, you basically have you have your regular exception levels. So you have EL0, which is like your user space, EL1 kernel, EL2 hypervisor, and EL3 is reserved for the secure monitor. Um, and you have this normal world and secure world. So normal world is untrusted, secure world is trusted. So the idea is even if somebody in normal world compromises the hypervisor, for example, they're not going to be able to like exfiltrate secrets or anything from the trust zone, because that's in its own isolated world. And it's just like another privilege barrier, basically. But of course, the normal world and the secure world have to be able to talk to each other, to be able to decrypt and verify and do whatever. So that's where the secure monitor comes into play. It bridges the communication there. It's also responsible for managing some of the critical peripherals. So that includes eFuses. Crypto engine and the replay protected memory block. So, of course, where it has access to such sensitive things and it bridges the communication, it's a very interesting target for attackers. So, yeah, they looked at it here. They found three vulnerabilities. First one they found was in the secure elements CMD high C factory check command. And what's notable about that command is it's one of a few secure element commands that don't check the arguments to ensure pointers to shared memory buffers are located in the safe area, which they denote as the CMA region. And as such, if the kernel can call it, which it can specify an address and size value that are outside of the CMA region and inside the secure monitor's own address space. So it's basically like a free corruption primitive because they just don't check the address that's coming in. Um, as they can get an arbitrary code and data size written to an address plus 4 and an address plus hex C, they have quite a few options they can go with there. They use it to smash the CMA address range and basically disable the CMA whitelist. And then they hijack a secure monitor call handler pointer, specifically BL31 SE cap handler. And that gives them some more primitives to work with, basically like a limited write. And they create a bit of a dispatcher based on the SMC ID to get a more stable read write primitive. Now they can't patch the SMC handlers directly at this point because the code is marked as read only. You do have to, bypass that write protection. But it was fairly trivial to get around that. They basically used their read write to target the page tables, created a second read write mapping to modify the code, sort of like how JIT works. You have like the executable mapping and the read write mapping. They just created their own read write mapping to get access to that. So with that, they modified another SMC handler to point to some shellcode, and they got code execution in EL3, which when you're talking about being able to access the critical peripherals, is a pretty significant break. Um, the second and third vuln was also in the secure element, though that time it was in the MNTN driver, which I believe stands for maintenance and testing. And it's through the logging functionality. So the second bug they talk about was another out of bounds access through SMC and NIT, which would take a buffer to do logging to. And they would try to check if the buffer address was in a safe range, wasn't pointing into the SMC address space. Problem is, it did so insufficiently when it came to integer overflows, because when they try to check against the upper bounds of the address space, they just add the size to it. And yeah, they don't have any checks against like if it wraps around or whatever. So pretty trivial in overflow there. There was also another bug which was very close and related to this one. And it's also extremely similar to the hypervisor vuln we covered before. And it's the fact that the log buffer in shared memory has a pointer that's used for logging, and it can be arbitrarily set by an attacker to point inside the SMC's own address space. It just doesn't validate it at all. So, yeah, they look at a few different primitives for exploiting this one. The one they focus on was basically getting an arbitrary memset through setting that pointer in the control structure. There was a few restrictions they had to deal with. For example, the size of the memset had to be smaller than hex 7b0 due to some basically restraints of the code and what it was doing. They also had to ensure that this get high C state function would return a non-zero value, which would only happen if bit 11 from this fixed address is set. So they exploited both of these vulnerabilities. Basically, they use the int overflow route to set this bit, and then they use the pointer switch to do the memset. From there, they use the memset to smash the least significant byte of a pointer to the handler of the same SMC handler as before, that SE cap SVC, and they use that to kickstart a job chain to get an arb right. And from there, it's basically the same chain that they use for the first bug. It's pretty much the same corruption logic. So yeah, I mean, some pretty interesting bugs. It's kind of funny that they had basically the same sort of issue in the secure monitor as they had in the hypervisor with logging. Seems like something that was just like thrown in for, doing quick development, trying to get quick debugging up and going, and just didn't really consider it as a attack surface for,
I mean,
attackers to hit.
I do understand developers kind of thinking that it's trusted data.
For
And
sure.
just not thinking about the attacker aspect of it. It does kind of make sense that it feels a little bit more trusted, but in the context here, like it may not be. Um,
Yeah.
I did like, honestly, just in the first part of this when they smashed the what was that? The basically the allowed address range when they
Oh,
just
the
smashed
CMA
that.
address range. Yeah.
Yeah, when they just smashed that range, I kind of just love that sort of attack. You see people do it in like the Linux kernel too, to make like user land accessible from the kernel and stuff. It's just such a fun thing to kind of abuse this to. I mean, you're not really abusing the security feature; you're just straight disabling it. But I don't know. There's something fun about that. I like seeing it. I guess I'll just say that.
Yeah. And jumping back a bit to what you were talking about with logging and it being trusted data. I mean, yeah, ideally, this logging functionality probably shouldn't even be enabled or accessible on retail builds. It just seems like a very unnecessary attack surface to put on the devices. But, it worked out for them. So that's kind of cool. And yeah, part of why I wanted to cover this one is we don't really see a ton of research into the secure monitor and things that are talking to the secure world, because generally a lot of end goals for exploits kind of end before then. Like, you don't necessarily need to attack the secure world depending on what you want. And also it's an area that's like not documented as well. There's not a lot of public code. There is like a public ARM reference, like the ARM trusted firmware, but of course vendors are going to extend on that and customize it. And generally, those aren't like well documented or public.
It's somewhat
So
hostile. Um,
exactly, yeah,
like
it's a good way of summarizing it.
yeah, it's not as easy to get into, to learn anything about, play around with, like, basically anything. There's that extra level, and that's kind of why I think they get away with what feels like stupid vulnerabilities.
Yeah. So it's always fun to see research into that area. Um, and of course, it does have quite a bit of an impact. Like, if you can start to read the fuses and those security sensitive peripherals, that's how you can end up like exfiltrating encryption keys and stuff, which can allow you to get further research done. So, yeah. I've really liked these posts by Impala Labs. I would recommend checking out the other ones too if you were interested in this area and mobile security. Because, yeah, they have the background on the hypervisor as their first post. Second post was the hypervisor Vuln we covered before, and then this is like the third in the series for secure monitor stuff. So, yeah, really good post by Impala. I think they're very understandable, even if you're not super familiar with Trust Zone or the context. They do a pretty good job of breaking it down through like the diagrams and everything. Um, and it may seem like a bit of a long read, but a lot of it is code snippets. It doesn't feel like it drags on really at any point. It gets to the point pretty quickly. So, yeah, definitely recommend it. Even if you're not interested in Huawei devices specifically, I think there is some knowledge here that can translate over into similar like devices and systems. So yeah,
And
there's a lot of cool stuff here.
I will quickly mention that it was just on like our last binary episode when we talked about the uh basically their other post.
Yeah.
So I'm just dropping that in the links there. But yeah, what episode 174 for that. But yeah, this post and the last one, both pretty solid, pretty understandable. Nice little graphs there.
Yeah. All right, so that's all the topics that we have for today. Z, if you have any parting thoughts, I'll let you go ahead here, but otherwise we'll wrap up the show.
Yeah, no shout outs, but I mean, since we're not going to be back until the new year, happy new year, happy holidays.
Yeah, exactly. So yeah, hopefully everyone has a good holidays while we're on break. You can catch the VOD on Twitch immediately or on other platforms like YouTube tomorrow. Feel free to join our Discord and follow us on Twitter. Even though we might not be around for the streams for the next couple of weeks, we will be around in the Discord. So if you want to, chat and whatever, we'll be there. Links for that are down below or in the chat. And yeah, once again, hope everyone enjoys the holiday and has a good Christmas and whatnot. And we'll see you all on January 9th and 10th when we return for the podcast. Until then, take care.